Sir T. Venktesan, Dr. Krishnan sir, all senior officers, we welcome for this lecture series and today's lecture is by Professor T. Venktesan and Professor Berrien. At the very outset, I would request our Secretary sir to kindly welcome Professor T. Venktesan and Professor Berrien by presenting a bouquet. So as you all know that we are celebrating this 150 years of establishment of India Meteorological Department, and during this celebration we are organizing this series of lectures by eminent speakers, and today's speakers are two very eminent personalities in their field, Professor T. Venktesan and Professor Berrien. Before we introduce our today's speakers, I would request our Secretary sir to kindly give a brief welcome address to this.
Okay, very good morning and of course good afternoon. And first and foremost, I thank Professor Venktesan as well as Professor Berrien for coming to, first of all, India as well as to IMD specifically, because we want to have, we were discussing for quite some time, at least more than 6 months. Professor Venktesan was behind because it started all how the expertise available from Oklahoma University as well as from other areas, how they can contribute to or collaborate with each other, especially we started with the radars and other things. And added advantages as Professor Berrien has come with, maybe you can listen, GeoCorp. It is a really mind-blowing instrument from satellite monitoring greenhouse gases. It is, I think, what is the technology he has developed and what is the status he will be briefing. And it is very great opportunity for all of us to listen from both of them. Of course, he is, though he has done many things from what is called starting from various physics fundamentals. Of course, he is a man of future. I mean, future means quantum. So quantum, which we have to heavily depend on in future computing and other things. So we can listen from Professor Venktesan also. So I think it is a coincidence with our 150 years of celebration of IMD, and it is a great honor to welcome both of you for readily agreeing and provide as a short notice on this talk about various aspects. I think unfortunately our DG has gone for some other minister has called, so he has gone. So he will join anytime if it is time permits. He will come there anytime. So without taking much time, maybe you can go ahead with the briefing about two of the author, then we can go for the presentation.
Perfect. Thank you. Thank you.
So I would request Anup to introduce our today's speakers.
Thank you so much, sir. Good afternoon and namaskar to all of you. I'm Dr. Anup Kumar Misra from India Meteorological Department, New Delhi, and I'm very happy to get an opportunity to introduce our speakers to the audience. We are honored to have Professor T. Venktesan and Professor Berrien with us. Professor T. Venktesan is currently with Center for Quantum Research and Technology, Professor of Physics and ECE at University of Oklahoma, and scientific affiliate at National Institute of Standards and Technology, Gettysburg. He's a senior advisor to the Office of Vice President for Research. As the inventor of pulsed laser deposition process, He has over 800 papers and 34 patents in terms of citation, over 58,000 with H-index of 121 in Google Scholar. He's a fellow of Royal Society. Yeah, he's a fellow of Royal Society, National Academy of Inventors, USA, and foreign members of Indian National Academy of Science, Singapore National Academy of Science, Asia Pacific Artificial Intelligence Academy, World Innovation Foundation, and American Physical Society, APS, Materials Research Society, MRS, and academician of Asia Pacific Academy of Materials, winner of Belcore Award of Excellence. And Professor Venktesan was awarded with George E. Peck Prize by American Physical Society, APS, in 2012, and distinguished lectureship on application of physics award, APS, 2020, and the President's Gold Medal of Institute of Physics, Singapore, guest professor at Tsinghua University, and past member of Physics Policy Committee, Washington, DC, and the Board of Visitors at UMD, and the chairman, Forum of Industry and Application of Physics at APS. He was awarded the Outstanding Alum Award for 2 IITs, IIT Kanpur in 2015 and IIT Kharagpur in 2016. He has founded 6 high technology startups and is the president of Neokera and CEO of Neokera Magma companies, manufacturing equipment for specialty coatings, pulse laser deposition systems, and semiconductor fault location using magnetic field imaging systems. And we have Professor Moore as our second speaker. And Professor Moore is an internationally recognized earth scientist who has been honored by National Aeronautics and Space Administration, NASA, and NOAA. He received his PhD in mathematics in 1969 from University of Virginia. And Professor Moore joined University of New Hampshire mathematics faculty in 1969 and become a tenured professor in 1976. He has recognized by University of New Hampshire in 1992 for research excellence and was named University Distinguished Professor in 1997. And Professor Moore served for Director of Institute for the Study of Earth, Ocean and Space at UNES during 1987 to 2008. In February 2008, Professor Moore left UNES to serve as the founding executive director of Climate Central, a think tank based in Princeton, New Jersey, which is dedicated for providing objective and understandable information about climate change. Professor Moore has published extensively on global carbon cycle, biogeochemistry, remote sensing, environmental and space policy, and mathematics. In December 2016, NASA selected Geostationary Carbon Cycle Observatory, that is GeoCarb, as the second Earth Venture mission. And Professor Moore is the architect and the principal investigator on GeoCarb mission. Professor Moore chaired the overarching scientific committee of International Geosphere Biosphere Program, that is IGBP, from 1998 to 2012, and as such led the July 2001 Open Science Conference on Global Change in Amsterdam, and is one of the 4 architects of Amsterdam Declaration on Global Change. And he was the coordinating lead author for final chapter, that is advancing our understanding of third assessment report of IPCC, which was released in spring 2001. And as such, he has been honored for contributing to the award of 2007 Nobel Peace Prize to the IPCC. He has contributed, yes, sir. Yeah, he has contributed actively to the committees, various committees at national. Yeah, in recognition of his lifelong dedication to the science, He has been the recipient of numerous awards and honors, including the NASA Distinguished Public Service Medal for Outstanding Service to the agency, NASA's highest civilian honor, and the NOAA Administrator's Recognition Award, and the 2007 Dryden Lectureship in Research Medal by the American Institute of Aeronautics and Astronautics. In 2017, Professor Moore received the Distinguished Alums Award from the University of North Carolina. He is an elected fellow of American Meteorological Society and International Academy of Astronautics. And please join me in welcoming Professor T. Venktesan and Professor Moore.
So, without spending much time, now I would request Professor T. Venkatesan to deliver his lecture.
Yeah, should I come?
So we can continue from there, or as you wish.
Yes, we shall. Actually,
As you wish.
if I want to point something, no?
Okay, that is.
Okay. Do you have a pointer?
Pointer will not work on this screen actually. So you can use mouse actually for.
So, actually, it's like, so, it all started about a year and a half ago, really. You know, I joined University of Oklahoma just about 3 years ago. And one of the main reasons I joined is because of this incredible weather program at the university. And also they had a phenomenal medical research program at the University of Oklahoma. Half of the university is actually a hospital with a clinician. And those are two big attractors for me to come to Oklahoma. And once I got there, the first thing I noticed was that in terms of the weather, I mean, University of Oklahoma has so much going on. I mean, it's really like a global epicenter for thinking about weathers, every aspect of weather. So I will cover more of the details in a few minutes. So it occurred to me that if I could forge an alliance between University of Oklahoma and India, between the two of us, we could probably, explore the most important challenge humanity is facing today: extreme weather and its devastating consequences. And you can see that why, because, for example, the World Bank, essentially World Economic Forum, listed the global risks along this chart, the impact of the global risk and the likelihood of the global risk. And you can see weapons of mass destruction is up here. Sorry. Oh, this is a touchscreen. Okay. All right. So you want to back foot? Yeah. So you can see the weapons of mass destruction is up here, but the probability, likelihood of it happening is very low. However, look at the extreme weather related events. They are comparable magnitude, if not even higher. But the problem is their probability of occurrence is very high, right? So this is like, it puts us in the right context, right? The extreme weather is as good as having weapons of mass destruction, and the only problem is we don't know where it's going to come from, when it's going to strike. And the only defense for humanity is basically ability to predict weather more accurately, right? And this has got to be a project of common concern to every citizen of this earth, every person on this earth. And it makes a lot of sense for the entire world to work together in solving this problem, right? So my thought was, why not we get a program between United States and India, get it started? So about a year ago, I came to India and I met with some professors in the Institute of Science, IIT Kharagpur. These are places that I was familiar with, and they all told me that you really got to talk to Dr. Mahapatra, the cyclone man. I said, what is this? This is like a superhero in India. So anyway, I came to Delhi. I met with Dr. Mahapatra, and he strongly advised me to get in touch with the secretary. And Ajay Sood, Professor Ajay Sood was my former friend at Institute of Science. So I met with him, and he put me in touch with Dr. Ravichandran. And he was very quickly responded to my initiative and said, get me a proposal from Oklahoma, So I went back to Oklahoma, and I immediately got in touch with Berrien Moore, because he was the director of the Weather Center, and so he was the key weather person in America. If you have to find one person, that's him. So I talked to Berrien and said, Berrien, we got to do this in India. And Berrien said, right on, let's do it. Count me in. And then I got the director of the Advanced Radar Research Center, Bob Palmer, and then we identified a professor, Pierre Kerstetter, to head up this program. So right now, we can already see. So I go to the next slide. Can you move? Okay. So what we realized was that what are the needs and significance for solving this weather-related problem? Regional risk awareness, these are the gaps in knowledge. Regional risk awareness with weather and water, observation and modeling, understanding of weather, water, and climate, and essentially operation to produce forecasts and long-term risk assessment. So these are kind of like the things that just about every country is facing, really. So let's go to the next slide. So what we said is, okay, I told all these people who are all interested in working on this India problem. 20 faculty members volunteered. They said, we want to work with India on this. They're very excited about it. These people range from essentially weather modeling, weather prediction, using AI/ML, and also people very interested in public policy making. In other words, how do you take weather-related matter and public policy, alerting people to the significance of, let's say, alerts coming from, let's say, the weather agencies, and people taking it seriously. Very often people ignore these things, right? So changing the public perception of weather as a very important part of their life, right? And taking weather as a very serious thing. So the people very interested in the public policy side of it. And then in addition to that, people interested in disaster management, like, okay, a disaster happened, then how do you prepare for a disaster, and then how do you take care of it? So there's all these different kind of people volunteered. So we thought we can really build a very big program with India, hitting it at different levels, right? So that was the idea. So this was the vision that we developed to help propel research entities in India and OU to the forefront of monitoring and forecasting climate and weather and water phenomena. So this is our vision statement that we made. The next, so what was our approach? I mean, our approach was to share effective climate and weather response and resilience in the system. I mean, for example, India has had traditionally monsoon and dealt with it for a long time to come, far more than any other country, right? So there's a lot of experience that India has got that the Americans can learn from, basically. So there could be a real mutual education by working together. So that was the idea. Co-create an ecosystem of academics and operating agencies. For example, in the United States, you go to the National Weather Center. The National Weather Center, the NOAA, very large, they're all located almost in the same building, right next to each other. And it's right on the university campus. So all the student, postdoc, it's kind of a very intermingled environment where, the academics and the national employees, they're all working together. And what it does is it adds to the brain power of solving these really difficult problems, basically, right? So this is what we would like to do, is to see how we can create a similar ecosystem even in India. That'd be really wonderful, right? And then the broader impact and collaboration, of course, once we take this model, the US-India model, we could basically replicate it in many other countries and make this into a global phenomenon. So that's the dream, right? Okay, next slide. So what are the benefits? Obviously, the benefit really for a society will create an innovative communication framework that exploits social media and other platforms to better inform the general public about weather threats on a variety of timescales. Severe weather, S2S, climate, that will increase the resilience of the society, right? I mean, particularly our now if you look at India, right, we have become one of the savviest country in terms of communication. We have the highest number of cell phones in this country, right? So for example, it's very easy for us to put, apps on the cell phone that will be completely weather related. Like in the state of Oklahoma, everybody has got a weather map on the cell phone, So everyone is really pretty aware of what the weather is going to be, right? And we can create a similar kind of an ecosystem in India very easily. and particularly for farmers, from the point of view of, seeding to, harvesting. I mean, they can really make some wise decisions and avoid a lot of wastage, right? So anyway, science, understanding extreme weather events and climate patterns, particularly, S2S, like, predicting weather in the longer time scale. I think Berrien will say more about it, but it's very complicated. I mean, it's easier to predict weather in a short term, but if you go to longer term, like, 6 months and 1 year term, that's really where, the real value lies, but it is also the most complicated to make the prediction. But India has a computing capability. We have, people who have the very good at software and, simulations and all of this stuff. So this could be a phenomenal collaboration between US and India to really say, how do we advance weather prediction to the next level, right? And that's where the science is, and this way we co-produce knowledge on a global level. Question is, why University of Oklahoma? The University of Oklahoma has real international scientific leadership in weather and climate. We have, cutting edge weather modeling and prediction work in everything from NWP, AIML, S2S, and also the Advanced Research, the Radar Research Center is one of the largest radar academic research related entity in the world. I mean, it's really, we have more than 75 world-class researchers working in one place, and this could be a great training place for training of a future radar experts in India, right? And then there's a rare, unique combination between private industry, academia, and the federal, all working in the same place. For example, multi-radar, multi-sensor group, which essentially designs the protocol for how do you get the data from satellite, radar, and the mesonet, and create this entire, national mosaic and feed this terabytes of information to a single, point. Essentially, data is now getting updated once every, 2 minutes, basically. And so that's all being done here on the campus here. And National Severe Storms Laboratory. And in addition to that, of course, Berrien Moore being the director of the National Weather Center, and he's also the Dean of School of Atmospheric and Geological Sciences, makes the university so close to these national organizations. So we also already have some collaborations with universities in India, primarily from people who graduated from OU and gone and become professors in India. But we also want to bring in other, institutes in the university, like Institute for Public Policy, Data Institute for Societal Challenges, and so on. So we have a lot of different people who can contribute. Okay, the next slide. So we created a big idea challenge. This is something that our Vice President for Research forces on us to think about big ideas and get people to, like, what we call convergent research. Like, you just don't think in terms of just physicists working with physicists. It's like, bringing people with multiple, expertise across the campus. And this is what called convergent research, which is where the entire US is moving towards the funding. And so this was our idea, basically. This program is now headed by Pierre Kerstetter. So our whole idea is about forging global alliances for climate, weather, and water, the example of India. That's what we put forward as our proposal, and our proposal actually won. But what that means is the university will put about $250,000 for 2 years to essentially get this program launched and moving along. It's like a seed fund, So all of these people have volunteered to be part of this program. And so next slide. So what are some of the exciting developments that are taking place? This, for example, the HORUS system. This is essentially next generation weather radar. It's essentially, I think, more than 1,000 element, essentially phased array antenna. The beauty of this is essentially right now, this will take the weather prediction, radar weather prediction, down to a few seconds from 2 minutes, right? So this is going to be the next generation stuff. It's not without its challenges, because the amount of data this generates is so phenomenal. How do you do this, actual taking the data and synthesizing it and all of that stuff? So those are all, pretty formidable problems, but they're being worked on, So this is very exciting. And so this will enable us to essentially do this weather mapping, and you literally get it real time, basically, like, because a few seconds, it's, so we'll be actually seeing it real time. And this is, of course, the National Weather Center, and the next adjoining building houses NOAA, basically. All right, next slide. So this is kind of what we're thinking of. So to create an ecosystem of academics and operational agencies in India, collaborating with them. So from OU side, we have look at things like economic impact of weather, weather damages. So the people want to work on economic aspect, societal policy making aspect, also weather climate related stuff, all the things from weather modeling, AIML, etc. And also infrastructure and urban environment, people are also wanting to get involved, okay? So, and we have right now, we have collaborations with IIT Delhi, Bombay, IIT Madras, Hyderabad, but these are all individual people, were working with the thing. And the big highlight is going to be the interactions with IIT-M, and we just we attended the Foundation Day last Sunday, which was a marvelous event there. And so we want to expand this further. Go ahead. So what we are now doing is we have developed a program called OU India Double PhD program. Okay. So this will enable a professor in OU and a professor in India to form a partnership, and they will jointly mentor a graduate student. Okay. And the student will spend over a 5-year period for a PhD, say 2 years in OU, 3 years in India, right? And it could be any 2 years, could be decided between the two professors, basically. And the professors will visit every year. One will go to the other place, the other will come to this place to actually make it into active collaboration, right, over a 5-year period, So this is what we want to promote next, and just create this real, because the graduate students are the exchange particles. I mean, they are the ones that really create relationships, So that's what we're going to do. So next, so the PhDs are, right now, both institutions will be able to offer PhD, and we work together then to offer a dual PhD program. 2 of the 5 years will be spent at OU. There'll be some course credits will be earned at OU, depending on, it's all completely flexible. And, and the travel costs of the faculty to be borne independently by each institution. And essentially, the OU will take care of the cost of the graduate student when they come to OU. And India will take care of the student costs here. And possibly the travel cost could be, maybe there could be some subsidy from this thing. That could be really helpful. Okay, so actually, just to give you an idea, for a graduate student per year, at OU, we have to put up about $47,650 per student. That's what we have to put up. And so for 2 years, we'll end up spending somewhere around $95,000, right? And the travel for visa for a student would be around $5,000. And sorry, go back. And so, and roughly travel of faculty to and fro from India would be around $25K over a 5-year period. So these are kind of the figures that we're talking about. So last part of it, this year I'm the Jubilee Chair Professor of the Indian Academy of Sciences. So I've been touring India. So I've been to now roughly about 8 to 10 places. And I've talked to the weather researchers all across, and I asked them, what are your biggest concerns, right? And so they all gave me some feedback. And so I'm going to show you what I got as a feedback. So please, these words are their words, not mine. So I'm going to do a declaration up front. So basically, they all feel very strongly that radar meteorology is an important subject for, and they would really like to see a collaboration enabled by MOES on a radar meteorology program could be very, very useful for the university, because they would like to kickstart the program and develop it to meet future needs of the country. Because we're going to need, if you're going to be expand to something like, right now with 39 radars, but you're talking about expanding beyond 80 or so, right? So which means that radar must be manned by real expert people, because, you need to keep them calibrated and make sure that the data is accurate and so on, right? So the radar management becomes a very important issue for the future, and we need manpower and expert, and we have to develop this workforce in India, right? So that's those are the things that this would be benefit from here. So next. So this is the kind of my last this thing. The recommendation to MOEs from them was, please make radar data available free of cost. It can be available on the net and downloadable by anyone without prior permission. Such system already exists in the MOAs, like the precipitation data, temperature data, the IMD reanalysis. And then only usage of the data by several scientists will provide feedback to the system and further develop it. Now there'll be like a feedback cycle where they can give input to the improving the system. And they all love the dual PhD program. And they said, wow, if we can get some travel support, we'd love to do this stuff. So this is all I wanted to say. Thank you very much. Take some questions, maybe.
Anybody has any questions
questions,
or
or-
clarifications?
So we have online participants also. So Anup, can you check in chat box and all that? Yeah.
Yeah, sure.
So in the first slide, you had used the term climate failure.
Yeah.
How do you really justify climate failure is a phenomenon, right?
Yeah. I don't know. I mean, I guess you can, I would say, like, for example, right, we knew, like in the Florida hurricane, right? People kind of knew almost till the last minute, they could predict the path of the hurricane, right? But in spite of that, the devastation that took place was unbelievable, right? And a lot of these were because, in places like North Carolina and many other places, there were building code violations, and things that they were actually overlooked, and they ended up paying a high penalty for it at that point. So something like that would be, I would call that a, weather-related failure, right? You just you ignore warnings and do something like that, right? And
Yeah, so last time also we discussed other things. So as I said, the Oklahoma University primarily focus area is on the radar thing, and as the IMD MOS, and we are going to enhance the radar thing. So that will be very technical. But in your slides, you are looking for the other area as well, water and climate, by engaging different professors, sir. So what are the planning other field other than the radar usage?
Yeah. Actually, in all honesty, Berrien can actually answer this question better than me, but almost every aspect of water, hydrology, weather, it's a very large population of people there, researchers in OU, right? Between the National Weather Center, NOAA, and the University Meteorology Department, it's the largest meteorology department in the country, one of the oldest department in the country. And there's a very large number of researchers covering, just about every area you can think of.
Okay.
Yeah.
Thank you.
So online participants are also requested to ask their questions if they have any.
So if there is no more question, then let us thank Professor.
Yeah. Thank you.
Now another very important talk. Actually, sir, recently WMO has initiated one program, Global Greenhouse Watch. And this year, India has given membership of that program. And very few countries are member of that program, and India is now one of the member. So in that regard, also this talk is very important, and we request Professor Berrien Moore to kindly deliver his talk.
Thank you very much. This is something that I've been working on since I went to the University of Oklahoma in 2010. In fact, in January of 2010, the American Meteorological Society was meeting in Atlanta, Georgia. And that is where my late wife grew up. It's where I grew up. And so I was staying with my mother-in-law for that meeting because I was in Atlanta and I had this idea about geocarb. So every night I would come back from the meeting and I could get nobody in the meeting interested in geocarb. Everyone thought it was crazy, which probably was, but everyone thought it was crazy. And my mother-in-law thought it was crazy. So I really had no one to talk to about this. But it's been a very interesting journey, and I'll share that with you. Next slide. I think everyone knows this. This is the Keeling record formed by David Keeling. He was a young postdoc in 1958, 59. And this was one of America's contributions to the International Geophysical Year, IGY, in 1957, 58. Is there a problem here?
No.
Okay. I won't go into the story, but it was recognized in that period of time that the idea about CO2, which was prevalent at the time, was you put CO2 in the atmosphere, it's just going to go in the ocean. Difference in partial pressure. And the oceans will mix. Put more CO2 in the atmosphere, it will go in the ocean. Roger Revelle and Hans Suess, Roger Revelle, very distinguished scientist, spent time in India, very distinguished scientist. They discovered that as CO2 enters seawater, it shifts the pH slightly downward. That decreases the solubility. They also realized that there was a back pressure formed from chemical reactions, which meant that CO2 wasn't just going to go in the ocean. Some would begin to build up in the atmosphere. So Roger Revelle went back to the Scripps Institution of Oceanography, got a young postdoc, David Keeling, and at Mauna Loa, which is the second highest mountain on the big island of Hawaii, in the middle of the Pacific Ocean, so very far removed from industry, very far removed from vegetation, they started measuring CO2 in the atmosphere. And this record, you see in this record two things that are very, very clear. The industrial metabolism of the planet, the industrial metabolism, the burning of fossil fuels, the industrial age. It's just nothing but the consequences of the industrial age. You also see the drawdown of CO2 going downward by the uptake of vegetation. Go to the next slide. Here you see it more clearly. We just blow up some of the record. So you see the drawdown. That's essentially the northern hemisphere's growing season, as CO2 is fixed by vegetation. And then in the winter and fall, as vegetation shuts down, as the leaves decompose, that CO2 goes back. So now you see the biological metabolic system of the planet, also the same record. It's just extraordinary to see this. Next slide. So what we now believe to be true, and this changes in time, but this is our best knowledge right now, is that a little less than half of the CO2 stays in the atmosphere, 47%, from fossil fuel burning and deforestation, land use change. Most of them from fossil fuel burning. About 31% goes into the terrestrial biosphere. Now, you just saw there's a lot of exchange with the terrestrial biosphere, but it goes in and it comes out, goes in, goes out. This is a net change. So there's somehow a net change of more and more carbon being accumulated into the terrestrial biomass. It could be CO2 fertilization, you make plants more water efficient. It could be an expansion of the growing seasons. We don't know. And about 26% go in the ocean. So it used to be 100% went in the ocean. Now we're down to about 25, a quarter goes in the ocean. But there are positive feedback loops. I just told you about the positive increases sea surface temperature, decreased solubility. That number can change with climate. Next slide. Here is, I think, a very beautiful slide. This is from the Dome Ice Core. The geoscientists of the world have discovered by drilling into ice, you can go back into time, and you can extract parts, little pieces of the atmosphere in the snow that fell in that year, and it's now down buried in ice. So you take out the ice core, it's like tree rings, and then you can begin to slice off the ice core, date it, and you see certain remarkable things. First of all, around the year 1000, the average CO2 in the atmosphere was around 280, goes up maybe 285, comes along, goes down. Why did it go down? Little ice age. Little ice age cooled off the ocean. Cool off the ocean, you increase the solubility of CO2 in seawater. So more CO2 goes in. So here you can see the feedback loop working to decrease. And it actually stays at, and so the effect of that cold ocean stays there for about 200 years. But then the Industrial Revolution occurs. And here's the ice core data running right into the David Keeling's record annually average. So you see, ice core record gives you a very accurate picture. Next slide. CO2 is not the only concern. There's methane. Methane, it's a very interesting gas. I mean, methane, the phenomenon of methane is very interesting. Suppose the microbes, the methanogens, suppose they did not exist. Just suppose. What would happen to the Earth? Well, slowly but steadily, all of the carbon would end up in wet, oxygen-poor areas. It wouldn't be oxidized. So the whole carbon system would shut down. Well, that would not be good. But methanogens take organic carbon in anaerobic environments and release it as methane. So there's no O, just H. And so here you see from the same ice cores, but notice how steady it was. There doesn't appear to be a little ice age effect on the methane because methane is scrubbed out of the atmosphere by the OH. So there was nothing happening here that was changing, about the same constant release, and then the Industrial Revolution. Now, methane, depending upon how long you want to consider, and you look at the global warming potential, methane on a per unit basis, it's a very strong greenhouse gas. Viewed over 100 years, it's about 28 times stronger than CO2. Next slide. But there's some things about methane that we don't understand. This is the global from Mauna Loa, same place at Keeling. So this is a globally averaged, averaged methane concentration. Why did it stop increasing in the atmosphere? Next slide. Here shows it a little bit more. Here's the rate of methane annual increase. Goes along, and then you see these little funny periods. Then it actually decreases in the atmosphere globally. Why? We don't know. Don't know. Very interesting. Next slide. I won't spend any time on this except to just point out two things. Methane is a much easier problem. There are really only two sources of methane. No, two anthropogenic sources. Fossil fuel production and landfills and cattle and agriculture. This is very different than CO2. CO2, there's sources everywhere. All the automobiles, all the airplanes, my barbecue. Anytime humans love fire. So there's CO2 everywhere. Methane is a much simpler problem. Much simpler. Next slide. So what do we know for sure, absolutely for sure, that CO2 has seen about a 50% growth rate in the atmosphere since the Industrial Revolution. Methane has nearly tripled, as you saw. Primarily fossil fuels, secondarily agriculture. Carbon dioxide is a very long-lived gas, so stabilizing it in the atmosphere is extremely difficult. Very long-lived gas. Next slide. Chemically active, so it's a short term in the atmosphere, maybe 9 years as opposed to very long term. If you take a 20-year, I just showed you the 100-year global. So take a 20-year record, then methane is really important because it's very strong, molecule for molecule, very strong. But it's the low-hanging fruit that human beings can maybe do something about, where CO2 is a much harder problem. And finally, we have to recognize that in all economies around the world, the use of fossil fuels is deeply ingrained in the economy. That's just reality. There are many people who say, oh, I don't want to believe that. Well, you may not want to believe it, but it's true. Next slide. Okay, climate is changing. Even in America with climate deniers, they say, well, climate's changing, but it has nothing to do with CO2. But, well, what does it have to do with that? It's changing more rapidly than we expected. The loss of Arctic sea ice was much more rapid than we expected. It's our human activity. It's not orbital dynamics like ice ages. Rational thing to do is we need to slow the warming down. So we need to get methane scrubbed out of the source terms we need to get at. But we got to make sure that we're also adapting. We have to be adapting. Next slide. I won't spend more time. I know we've got a lot of things here, but I do want to point out one thing that I have to say to my friends in the United States. They all run around and buy electric cars, particularly in California. They all talk about their electric cars. And I said, well, it's wonderful, your electric car. I love that electric car. But you realize when you plug it in, a coal-fired power plant in Nevada gives you the electrons. So it's a feel-good strategy. It makes you think when you're driving around, I'm not burning any fossil fuel. Oh, yes, I'm just burning it in Nevada. Next slide. I think we have to recognize that this climate business is a system of systems. It's a problem of problems. You've got to take a systems view. You have to look at the consequences of alternatives. We have to be prepared for surprises, but that's hard to be prepared for surprises if you don't. I mean, I'm surprised when I have a birthday and my daughter says, well, I'm surprised, but I'm not really surprised. Real surprises like the Arctic sea ice change. That's hard. Next slide. I'm going to go ahead and just simply, I think I've talked enough about that. Let's go to the next slide. I want to talk to my friend. Next slide. Okay. In 2010, the Orbiting Carbon Observatory 2, well, actually, they were building it. They hadn't launched it, but and I love the acronym, the Orbiting Carbon Observatory, OCO, CO2. Very, very clever acronym. JPL built it. It's a very interesting mission, but it's in low Earth orbit, and the swath, in terms of using the reflected light to determine how much CO2 was in the atmosphere, the swath is only 10 kilometers wide. And then the next time around the planet, it'll be 1,500 kilometers to the west. So I started looking at that, and I said, if there was some way where we could just repeat that swath, in other words, not have it. So then that suggested geostationary orbit. Next slide. So here's an animation of how CO2 works, how it works. See if that, maybe it'll be, maybe you have to click it again. Oh, here. So what we have is we have optics with a slit. And the slit, when I project it down onto the ground, is about 7 kilometers wide, 2,200 kilometers north-south. If I stare for 9 seconds through that slit, I get the signal to noise of OCO. So the idea that we have, if this can show, I don't know if it will. Will this work here? It has to be in slide. It has to be in slideshow. It has to be in slideshow.
So this will not work. So this will not work.
I think that requires some.
Especially that media.
It won't show. Okay. All right. Well, that. Okay. So here's an example of geocarb. We have this slit in the optics. And so if I stare with this slit for 9 seconds, and then that slit is 2,200 kilometers. That slit is 22. So I break the slit up into little 6-kilometer boxes, north-south. It's 6 kilometers east-west. Now, of course, as you go to the, it gets wider. But then I stare for 9 seconds and then I move it over. Stare for 9 seconds, then move it over. So this takes about 2.3 hours. This takes about 144 minutes to do this. So, and I can move it anywhere. We could, for instance, we could just do this and this, not do the rest of it. Or we could just do this. Or we could just do this. So if I just did this right here, I could measure the United States. I could go wall to wall, about 8 times a day. If I just did the middle of the United States, like the Corn Belt, I could do that 16 times in a day. So I'm measuring it 16 times as opposed to once every 14 days, which OCO is doing. And so here's an example I take Mexico City. Here's OCO coming through on, shall we say, day 1. 7 days later, OCO comes through here. 7 days later, here. Geocarp every day, wall to wall, every day. To try and determine how much CO2 or methane is coming from Mexico City with twice monthly, very tough, very tough. Let's go, next slide. So the idea was to fly geocarp, this is the mission, and to make a fundamental advance in our knowledge of the carbon cycle and the methane cycle. Also to demonstrate technologically verification tools to verify what countries were saying. Next slide. So here's what the instrument looks like, and I'll come back to this. I know this looks rather funny. You say it's upside down. Well, it is upside down, but it's looking down at the Earth. So here's a telescope, and here's that thing that causes the optics to scan. And we have a spectrometer with 4 wavelengths. Here are the 4 wavelengths: oxygen, CO2, methane, CO. Why am I measuring oxygen? Well, I want a concentration measure. For these 2 wavelengths, I get a total CO2, total amount of CO2 in a column of air. But when I go over mountains, I have less of a column of air. I don't really have less CO2, I just have less air. So to make calculations, you want a concentration measurement, not just total amount. You want a concentration. So we measure the total amount of oxygen. So we measure the total amount of oxygen. And that's what this spectrograph does. We're using, I won't spend much time. We're using kind of an old design, which I'll come back to. Next slide, let's go ahead. So this is what you saw earlier. This is what we're going to, this is the geocarb. We are in 90 degrees west longitude. We're right about here. We're on the equator. All geostationary satellites are on the equator. We're about due south of New Orleans, the city of New Orleans in the United States. These are basic, but you could put geocarb here. You could put it at 70 degrees east. Your weather satellite, I just learned today, is at 84 east. So this is a slot. This is a longitudinal slot you know very well. And these are the places you could scan. Now you could change this around. You could say, well, I'm not interested in this. I'm just going to focus more here. In other words, you can move the scan strategies anywhere. Well, anywhere in this region. You could put it at 110 east, basically over Singapore. And you could then scan Australia, China, Southeast Asia. You see some of the same here. See some of the same here. Next slide. Well, I'm suggesting the obvious. It would really be important if we need a global carbon observing system. You need all 3 slots filled. There's interest in Japan on maybe about doing the 110 East slot. This would be a natural for India to lead. Next slide. I want. These are just the questions that we're asking. We're asking all the basic questions. You know, how much anthropogenic CO2 is coming? How much is coming from methane? So how much anthropogenic, and then how much natural systems are doing? Those are the questions. Next slide. This is the important slide. This is a very tough measurement to make. This is the total concentration of CO2. I got to be 99.7 sure from 36,000 kilometers away. That's the challenge. Likewise, with methane, in parts per billion, methane's in parts per billion. These are challenging numbers. CO, not quite as challenging. We also measure something called solar-induced fluorescence, which gives you a measure of vegetation activity. We see that in the oxygen measurement. Next slide. Okay, why geocarbon? Persistence and preciseness. I just showed you the precision. That's essential because the information is in the gradient of the concentrations. The information is in the gradient of the concentrations. If there were no gradient in the concentrations, you wouldn't get very much information about sources and sinks. It would kind of say, well, there's no gradient. Well, we know there's gradients in sources and sinks. But so the information is in the gradient. That's why you have to have high precision. The other thing is you're there all the time. You're persistent. You're there every day. You're looking at fugitive methane. If you're looking for that, you need to be looking at the United States every day, not once or twice or 3 times a month. You'll never see fugitive methane. Is what leaks out. That's well named. It's fugitive. It's hard to see. Next slide. Also, proactive. You need to be able to adjust your scans. You say, oh, there's forest fires happening here in Brazil. Let's look there. Let's map that so we can be proactive. We could whereas if you're in low Earth orbit, your crossing times are you're coming over at 1:30 in the afternoon. In fact, we were told that there was people who were burning forests. They wait until OCO goes by and then they burn the forest. Got to be wall to wall. You need to measure terrestrially, you need to measure wall to wall. Next slide. This just simply shows this idea. I'll talk to you later if we have time. We'll talk about the solar-induced fluorescence. I think it's extremely valuable. It gives you a measure of vegetation health. Also, solar-induced fluorescence is in that near oxygen band. Clouds are transparent. So we can measure solar-induced fluorescence irregardless of cloud cover. That means we're measuring, every time we're looking at the Earth measuring CO2 and methane and CO, we're seeing solar-induced fluorescence because the clouds don't matter, which is very powerful. Next slide. Okay, now you'll see it. Next slide. Okay, here's the instrument. These are star trackers. Here is the telescope with the lid down. Here's with the telescope lid up. We want to fly it with the lid up. We close the lid at night, then open it up in the daytime. Next slide. Next slide. What if we did another one? Based on the mistakes I made, we could simplify the spectrometer tremendously. We use a grading spectrometer, which was what we had available when we did the start of the vision. This can be simplified. And hence the whole scan box can be made much simpler. The optics can be greatly reduced. When we built it, we didn't know what kind of spacecraft we were going, so we had to build these radiators. No, get rid of that. The spacecraft will take care of that. We were going on a hosted payload, so we had to have our own radiators. You can simplify the optics. The cryo cooler is it's a commercial cryo cooler, which you can do now. Just buy it off the shelf from Northrop Grumman. Get rid of that one too. But here's the big deal. All the algorithms are done. So we can go produce from radiances, level 1A, we do all the corrections, the atmospheric corrections, all that is level 2, making concentrations, all the, so go from radiances to concentration. All those algorithms are done. And then from level 2 to level 4, we get fluxes. All those algorithms are done. Second time around, this is vastly easier. Next slide. Okay, this was a great day. It was August of 2023. Now, I'll be very honest with you. In November of 2022, the mission was canceled because we were way over budget. And NASA said two things. They said, we do not think you can build it with your remaining resources. And I said, well, don't take them away. Let me see if I can complete the instrument with the remaining. You NASA have decided that. I haven't decided that. If I thought that, I'd give you money back. Fortunately, they left me with the money. And secondly, they said, well, we don't have a way to get you to space because the hosted payloads and geostationary and Elon Musk has got Starlight up there, and it's a whole different world. That's still an issue. I'll come back to it. Well, here we are. That was November 22nd of 2022. The instrument's built. Next slide. So we took it down to the large thermal vacuum chamber, which normally you put a whole spacecraft into. This is at Lockheed Martin at Mountain View, California. Here's GeoCarb. Here's the telescope. The other star trackers on the other side. Here's the spectrograph. Here the mounts, the plate, the whole thing mounts onto the bottom of the spacecraft. Next slide. So you can see little GeoCarb instrument. It's kind of lost. We weigh about 157 kilos. It's about a meter by a meter, about 3/4 of a meter. Next slide. Here we're making some last minute adjustments, including for me telling them, open the telescope. Don't close the telescope because we're going to make measurements in the thermal vac chamber. Next slide. So here we are. We've finished thermal vac, and we're sitting here ready to pack everything up. Next slide. And so I packaged everything to ship to NASA, and I thought it was almost in the holiday season. So I put a little Christmas wrapping on the spacecraft. Next slide. And this was the day that the shipping was to occur. And this is a slide that NASA is not very happy with, because we had a professional photographer. You know how professional photographers, you've all been, they take a group picture and they tell the group, no, you move here, you move here. They tell her, and everyone just does it. And so they told everybody, all these are NASA people. They said, everyone kind of look a little bit towards the middle here. Here was the program manager, here's my deputy. And they all said, do this. All the NASA people. Now, this is an instrument they canceled. So they're all going like this. Next slide. So we're going to bring this back. This would be, I think I may rename it the Phoenix Bird satellite. What's very interesting, how the world happens, how just things happen. 25 years ago, I was at the University of New Hampshire, and I was leading the Institute for Earth, Ocean, Space Science at the University of New Hampshire. And I hired a very good marine biologist, Joe Salisbury, very good marine biologist. So in 28, 29, I left New Hampshire, went to Princeton for a short period of time, then went out to Oklahoma. Proposed GeoCarb, and eventually it was selected. And Joe Salisbury is also interested in marine biology, and he's proposing, after GeoCarb, he's proposing a geostationary satellite that would look at the Gulf of Mexico. It's called GLIMR, G-L-I-M-R. It looks at the ocean in 25 spectral bands. It's not trying to determine anything about the atmosphere. It's just looking right at the color of the ocean in 25 wavelengths. And so it was selected. It needs a spacecraft. I need a spacecraft. So my student, or the person I hired, he needs a spacecraft. I need a spacecraft. There was a mission which the payload got into trouble, and so the mission was canceled. It was a geostationary. So now you have a geostationary satellite that the American government has already bought. And Glimmer and Geocarb want to go to the same orbit. And we fit onto the spacecraft. So now the hope is, it's not official, but the hope is that we launch in the spring of 26. That we do calibration characterization late next summer. We're working on a few technical issues right now, and we have a contract with NASA to solve those technical issues. It deals with data processing, which we can solve. And then we will do calibration characterization where you characterize the errors in the instrument. And every pixel on the CCDs are characterized. And then we go up together. So thank you very much. It's delightful to be here. Be happy to answer any questions. I know we're out of time, but.
Yes. So the floor is now open for questions. And Anup, check online also chat.
Online participants are also requested to ask their questions if they have.
So Professor Berrien, I have a small question from you.
Sure.
We can measure the total columnar carbon dioxide using satellite measurements. But is there any way we can estimate the surface concentration also?
Well, I think, yes. Let me answer the question two ways. First of all, it's essential that we have ground-based truth in locations. That's absolutely essential that we have that. And we need it for CO2, CO, and methane. And there is something called the TCON, Total Carbon Observing Network. It has about 30 stations around the world, which have a spectrometer that looks it up and measures the same thing, but just takes, the light coming, doesn't measure the reflected light. So it's a ground-based. That's very useful. And then secondly, and you have this in India, you have about 10 or 12 field sites in forests and native ecosystems where they're measuring CO2, methane, CO. I don't know about CO, but I know methane and CO2. Those TCON stations at these field sites are essential for final calibration characterization of the OCO uses that. But they have to be, they don't get to check their calendar. They have the same problem with, they don't go by the TCON site, but maybe once every 20 days. So the more sites you have, but then with geostationary, you can wall to wall. So you can look at different places, and that is really valuable.
So you need a better ground stations for estimating the surface concentration using satellite also.
This is a little bit like asking a biologist about how many field stations you need. They say more. So the answer is always more. I think that what you have in India maybe another 50% increase. That would be wise. But I think that we're working with Peru about establishing some ground sites in Peru. So we want some in South America, not just in the United States. I think that if you go, if you really were able to get India Geocard going up, then I think you would actually like to work with other locations. But you must remember, you will be seeing things that have enormous importance. You'll be looking at Saudi Arabia, you'll be looking at the Middle East. And you'll be looking directly at where methane leakage occurs. And you would get a measurement of that. So this will be, measuring CO2 and methane is also, it has a political ramification. It's a policy ramification. Countries have signed the methane pledge. Nobody's on it. nobody is even getting close to fulfilling the methane pledge. But there will come a time when we will have to verify and validate what countries say they're going to do. That means you've got to have an observing network. I mean, that's just the way it is. Also, we know that for terrestrial systems, but also for methane, it'd be very interesting in India to look after monsoon, how much methane comes out of wetlands. You know, during the peak of monsoon, because you have so much rainfall, there'd be no methane coming out. But as that water begins to leave and you start opening up those wetlands, it would be interesting to see. I would imagine you'd see a large pulse of methane coming out. I don't know that. We have to make the measurements.
Berrien, you also mentioned about the Western China.
Second,
The Western China part.
well,
Very interesting.
let me say this, that without going into any detail, if you are emitting CO2 or methane and you don't want to advertise that, and you know that a LEO spacecraft is going to come over, you know exactly what, I mean, this is not an uncertainty. You know exactly when that LEO spacecraft is going to come over and your power plant is visible. If you put a lot of water into the stack of a power plant, you put a lot of water vapor into the atmosphere and you will not see from space any CO2 because you will have flooded the atmosphere with water vapor and aerosols. So trust, I mean, the verification issue is going to require geostationary. I mean, that's just obvious because you've got to be able to watch it every day. And if you want to help, I mean, the natural gas companies in the United States, if you realize Oklahoma is right in the middle of the natural gas producing area, they're all very much in favor of geocarbon. Because for them, as one of the oil and gas persons said to me, he said, everyone says that methane is colorless. He said, no, methane is green, just like a dollar bill. It's not colorless, it's money. It's $1 billion loss in the United States from the leakage of methane. $1 billion. It also makes natural gas less desirable fuel of transition from coal to natural gas if you have all this fugitive methane. So it's a problem that we have to solve. Yeah.
Question is regarding removal of these greenhouse gases from the atmosphere. So what is the status of any technological development is there? Had it been there, from the source itself, we could have removed. Why, if not there, why there is a difficulty such in technology?
Well, let me answer that question in 2 or 3 ways. One, there are strategies of reforesting areas or putting forest, what's called afforestation, putting a forest where there was a grassland. So increasing forest cover. Now there's a little bit of a negative feedback, a little bit of a positive feedback. You darken the planet slightly, so you decrease the reflectivity. So that you have to think about that. But growing trees is one thing. Secondly, you could be paid. We pay farmers to do all kinds of things. You could pay farmers to try to store carbon in soils by increasing the amount of vegetative material in soils. Farmers, they plant peas, or I forget what the crop is, that fixes nitrogen, and then they plow that under, so they actually get nitrogen out of the soil, out of the sky, and then they convert it back into the soils. There are ways in which you could pay farmers to store carbon. The other thing that you could do, but I don't like this, is I spent some time at Woods Hole Oceanographic. It was actually when I went from theoretical mathematics to science. And so Woods Hole Oceanographic Institution is looking at the following problems: is to go and try to raise the pH by chemical ingredients, alkalis, dumping them into the ocean. And that means that you increase the solubility. Well, yes, but then that means you put more CO2 in the ocean, which is what they're trying to do. But then now that's going to decrease the solubility. So that means you got to put more of this alkali into the ocean. So now you are in what we call a Faustian market. You now have to keep feeding the ocean. And the ecological ramifications, what this does, I think it's crazy. There are other things you can do, and I think this is where natural gas replace coal with natural gas, then take the reduced amount of CO2 coming out of the stack, try to strip it out, and then bury it or store it. So then you can go to power plants. That works in power plants, but it doesn't work at an electricity generating station. I mean, an airplane. It's not, so you still have to worry about a whole lot of other sources of CO2. But I do think we're going to have to think about this. Because CO2 is so hard to stabilize in the atmosphere, we're going to have to think about this. Yeah.
Will this instrument be useful in the monitoring the health of the vegetation?
Say again?
Health of the vegetation.
Oh, yeah, that's what we think is extremely valuable. This solar-induced fluorescence, what happens is vegetation needs the ability to put up an umbrella and say, I've had enough energy for today. Because the sun keeps coming. So vegetation does not have an umbrella to stop. So it has to have some way of getting rid of energy. So vegetation fluoresces. It fluoresces in that oxygen band. All vegetation fluoresces. It fluoresces at different rates depending upon the type of vegetation. We'll see that fluorescence. If you see a shift in the fluorescence, and for instance, we will look at the corn belt of the United States and the wheat growing here every day. Sometimes we'll look at multiple times a day. So if we see any change that could indicate water stress, or could indicate disease, or it could be tied to the little calculation that I went past, I don't want to spend time with it, shows that you could actually look at solar-induced fluorescence and get a yield projection. So if you can now begin to put that into agricultural policy, here's what we think our yield would be. I think the solar-induced fluorescence is going to be as valuable. Well, no, I think CO2 and methane would be the most, but it'll be a very valuable piece of information. And we already know this is possible. OCO measures solar-induced fluorescence, but it's just a little narrow swath. So that's not really of any use for agriculture. It's too small. And it only, like every 7 days, every 14 days. So for the farmer, it's just too little information. But geocarb's wall to wall every day. And sun and the clouds are transparent. So every day you'll make a measurement at 6 kilometer by 6 kilometer.
So all the spectral band having the same resolution or different?
Say again?
Or you mentioned the spectral bands. All the spectral bands having the same resolution or different resolutions?
I'm not following. Spectral bands?
Spectral bands you were told, no? You were mentioned in the spectral band.
Yeah. Well, they're four
The
spectral bands.
wavelength bands.
Right. And we use a grading spectrometer to separate out the color of light. Vinky thinks that maybe the next geocarp doesn't even maybe need it may not need to be a spectrometer. What if you could just put a filter on the light coming in? And the filter gets rid of everything except 0.76 nanometers for oxygen or 1.47 for CO2. So maybe you could just do this with 4 filters. Not use the it's not a spectrograph. I'm not sure what it is. It's just a telescope with filters. That's a very interesting idea. I think the fact that we used a grading spectrometer, the particular one we used was not the best choice. I think I've seen new papers about better ways of creating the spectrum. We just made maybe the wrong decision. There's been some real advances. The other thing is the optics. The optic could be much simpler than what we designed. We just didn't think hard enough about the problem. Anytime you're doing something for the first time, to give myself some excuse. You just make mistakes. And we got into a situation where we were concerned about how heavy we were. And logically, it should not have been a concern, but the spacecraft company was putting pressure on us to reduce the weight. They wanted to make more money. And so we cut the optics in size. And then we found that, yeah, all the optics were much smaller, but now mounting the optics was about twice or 3 times the difference because they were so small. So here we did something thinking we're saving weight, and we increased the problem of integration by a factor of 10. And you don't make that mistake twice. I mean, the next geocarbon, vastly simpler.
So let us thank
Online participants, if you have your queries or questions, you may please put up.
Second?
I don't know, there are participants, there are online participants, so we are just requesting if there are any.
On the chat box,
I couldn't see what they said.
Nothing is there in chat box.
So let us thank Professor Mood.
Thank you very much. Let me just say how honored I am to be here. This is my first trip to India. And I've always wanted to come here. Even as a child, I wanted to come here. And I read all the stories about India, and the scientific expertise in this country is enormous. It's really quite exciting to see the science. And the fact that you have so many young scientists, that is really, really important. You've attracted really good young scientists. That's a big plus for India, big plus. Thank you.
Sir, Professor Venktesan and Professor Moore visited few divisions, IMD, and but that was not enough. So Professor Venktesan requested that he will come back again later part of the day and visit another sections here. So we welcome you, sir, after your meeting with PSA. Again, we will be very happy to host you here again in IMDA. So I would request our DGM sir to say a few words before we wrap up the function.
Now, I think we are all proud and privileged with the presence of Dr. Venktesan and Dr. Berrien. And this is the initiative of respected Secretary Dr. Ravichandran, through which we could realize today's special lecture by the 2 eminent experts globally. I'm sure that it has benefited all of us, and especially the young minds, as you told, the young scientists in India and outside. People are joining this program through YouTube and also the various web channels. It will certainly be beneficial while we think about the future plans. It's very much futuristic. And already Dr. Venkatesh always speak about the future, and we are planning a lot of activities in the Ministry of Arts Sciences with able guidance of Secretary and IMD and 7WF and many others are involved in that. We'll carry forward the thoughts which have been shared today. I feel really very happy while going through the various lecture series to celebrate the 150 years of IMD. So this is an occasion where we are celebrating all the stalwarts, those who are participating with us and delivering the lectures, educating us, and carrying forward the message of serving the society through the knowledge.
Yes.
So thank you very much. It is already delayed. So on behalf of all of you, I thank Dr. Berrien and Dr. Venkatesh making available for this. I also thank Dr. Ravichandran, Secretary of Ministry of Arts Sciences, for his inspirations, guidance, and always the thought behind any initiative taken by India Meteorological Department. Thank you very much, sir. Thank you very much.
So it's a time to express our gratitude to speakers. I would request Secretary sir to felicitate by presenting a bouquet, shawl to our speakers. I request our DDM sir to kindly present the memento to our guest speakers. Thank you. So very quickly, I express our, on behalf of Ministry of Earth Sciences, India Meteorological Department, and on my own behalf, I express our sincere thanks and gratitude to the speakers, today's speakers, Professor T. Venktesan and Professor Berrien Muri. And also thank Secretary Sir, DGM Sir, and all senior officers who kindly joined us today. So thank you all.